what we're looking towards is finding areas under curves. So if you had a sine curve like this and you wanted to find the area under that curve to the x-axis, it would be difficult because we don't have a formula that says, oh, that's, what would you call that shape? I don't even know if that has a name, right? It doesn't quite look like a trapezoid. It's not a quadrilateral. It's not a triangle. It's a shape we don't have a name for. And if we have a shape that we don't have a name for, we probably don't have a formula for finding the area of a shape we don't know what it's called. We have areas for squares, we have areas for triangles, we have areas for circles, but we don't have area for funny looking shapes. And that's where we're going towards. How do we find these areas for funny looking shapes? Well, the idea is, well, I know how to find the area of a rectangle. So if instead of finding this area S exactly, because I don't have a formula for that, I'm going to split it up into a bunch of little rectangles. And the little yellow rectangles that are there are all underneath the curve. So we could say that if we calculated all of those rectangles, our area would be a little bit too small. But if we made those rectangles smaller, our area would be more accurate, but still too small. And if we made it smaller yet, it would become more accurate, but still not quite there. If we kept doing it until they got so tiny that it's so close to being accurate that it would be right, we could say, hey, that's a pretty good estimate. Or we could even say it's close enough, so close that I would say it is right. So if we keep making those rectangles smaller and smaller and smaller, perhaps we get the right answer. So we do an analysis. I take one of those little rectangles and I look at it. Okay? The gray part is the actual area. And here I have one rectangle that's smaller. So on our original graph, this was colored in yellow. And one rectangle which uses the top point, which is bigger. So if we made a rectangle with the highest point and a rectangle with the lowest point on the function, then we would get a rectangle whose area is too small, the blue one, and a rectangle whose area is too big, the green one. And our actual area is somewhere between the blue rectangle and the green rectangle. So we write this out. We know that an area formula for rectangles is length times width. So a couple of notation things here. I'm calling this part dx with a fancier Greek-looking d thing. I'm calling this height here y up to there, and this extra height dy. And so length times width, the blue rectangle is y times dx. That's smaller than the actual area, which is smaller than the big green area. Now, if we divide each of these by dx, I get y is less than dA dx is less than y plus dy. And here we're going to think about, well, what does dA dx mean if you're doing it smaller and smaller and smaller? That's basically a derivative. That's a change of area with change of x, the derivative. And as you get smaller and smaller rectangles, as that dx goes to 0, can you see that your dy on your original graph, as you get closer and closer going this way, that your point would come down here and your dy would also get smaller and smaller. In fact, as you made it go to 0, your dy would also go to 0. Oops. And so this equation, as this goes to 0, this becomes our derivative. And as this goes to 0, dy goes to 0. So our equation simplifies to just be that y is less than dA dx is less than y. Now, have you ever had an inequality like that before? It's a very interesting inequality. If something, okay, let's put numbers into here. If 5 is less than something is less than 5, what number would you put between 5 and 5? What would fit in there? 5. Would anything else fit in there? No. So if this dA dx is supposed to be between those two, and they're the same thing, that's basically telling us that y has to equal dA dx. If you think about that theoretically, as we make our rectangles smaller and smaller and smaller, our area becomes basically the same as the height. It's just that thin, thin, thin line. Now, if we integrated both sides, what that allows us to do is it says, well, integrating a derivative would just get us a. And a stands for our area. And integrating this side is an integral. And so it's basically saying if we want to find the area under that curve, we just need to find the integral of that curve. In particular, we're going to look at what that area does. It gives us an area from the origin up to any value, but we're going to pick certain values to figure it out in between. In our example, if you want to figure out between A and B, if I plug in B, it figures the area all the way down to 0. If I plug in A, it'll figure out the area all the way down to 0. So if I want to find the area in between A and B, I could take all the way down to 0 here and then subtract this area, leaving me with just the area between A and B. So we do the area up to B minus the area up to A. And this is called the definite integral. The definite integral, the way that we write it, it's just like our integrals from before, except we put values of A and B on the top and bottom of the integral. So it's telling us that we're starting from this point A and going to this point B. And we're finding the area under the curve from there to there. So how do we find our definite integral? We find our indefinite integral like before, but we do not need to have a plus c anymore, because when you're subtracting, one c minus another c would just go away. So we don't even write the plus c with a definite integral. We find our integral, and we put it in a square brackets and write from a to b in there. Then we plug in b and plug in a and subtract the two to find a value. I know I have an example A there, but I thought we could start with a really easy example to see what's happening. Okay? An example so easy that you could even figure out the area without any integration. So I'm just going to draw the line y equals x. And if we went from 2 to 5, we'd have the point 2, 2, we'd have the point 5, 5. If you wanted to find this area, And one thing you'll learn is I love coloring in areas with crayons. It really is just enjoyable, the Smartboard crayon. If I wanted to find that area, and I didn't want to use any other formulas, can you see that you could easily separate this into a rectangle and a triangle? That this length is 3, this length here is 2, and this length here is 3 as well. And the area would be that rectangle plus the triangle. How do we find an area of a rectangle? Length times width. So this would have an area of 6. And how do I find the area of a triangle? Base times height divided by 2. So 9 divided by 2. This would have an area of 4.5. Total area of 10.5. Now, according to our idea of definite integral, I should be able to find this area by doing the indefinite integral between 2 and 5 of, what's my function? X dx. My area should equal that. Now, I chose this because it's a really easy integral to do. With a definite integral, we figure out our integral and put it inside of a square box instead of writing plus c. Well, add 1 to the exponent and divide. And we still go from 2 to 5, and we write those numbers beside the square box. You then plug in the 5, 25 over 2. Plug in the 2, 4 over 2. Subtract, giving us 21 over 2. So I guess it didn't work, because we got 21 over 2, and the actual area was 10.5. Or wait a minute, it did work. Whew. We got the same answer without having to separate it into different shapes. And in fact, the integration and the math that we had to do was really quite simple in this case. But we had a simple equation. The beautiful thing is that this is going to work no matter what equation we have. And we can figure out all sorts of complicated areas that everything we would have used up till now wouldn't have helped us. So let's look at our actual example. First example, which is the integral from 2 to 5 of 3 over x. Sometimes it's fun to draw these. There we go. We want to figure out, on that curving graph, this area. And it's not a straight line anymore, it's a curve. So it doesn't look very pretty at all. Well, how do we do it? We go and we need to integrate. I went and started off with a mediocre integral. This one can be tricky because it looks like a power rule, but in reality it is a natural log. 3 natural log of x. So our area would then be, plug in the 5, plug in the 2. If we didn't have a calculator, we could leave our answer like that. Do you remember all of your exponent laws? What could I do with the 3's out in front? I could put them as powers. So I could write this as 5 cubed minus, 2 cubed. What can I do when I subtract two logarithms? Divide. If I evaluated 5 cubed, that would be 125. And if I evaluated 2 cubed, that would be 8. Often on university exams, they'll say you can write your answer and leave it as a logarithm, but we want a single logarithm with just one number in there and simplified. They have all these rules for how you write your final answer so they don't have to check if you're right or wrong, because it should all look the same. This would be considered one fraction inside of the natural log, and you can't reduce that fraction, so you would be fine. Now you could estimate what you think that looks like, 15 or something. So it's going to be an answer between 2 and 3. But a very weird looking answer, and yet we just calculated that orange area perfectly. Which is kind of cool, because it wasn't an easy area that we could figure out otherwise. We still have to worry about all the issues of integration that we had from before. So in this second example, how are we going to integrate x plus 1 over x squared? Probably expanded out is not a bad idea. You could be thinking substitution, you could be thinking integration by parts, but in this case, actually multiplying it out is going to be the best. If I multiply it out, I'm going to get x squared plus 2 plus 1 over x squared. If you want to somewhere off to the side write it out and draw all the arrows. Whoops, that's too many arrows. But you get the idea. You could multiply that out somewhere else. The x times the 1 over x is just 1. You would have that happen twice. That's why I get the plus 2 in the middle. Dx. And now each of these is easy to integrate. We would get x cubed over 3 plus 2x plus x to the negative 1 over negative 1. Add 1 to the exponent and divide. Plug in the 4. So you're going to get 4 cubed over 3 plus 8 minus 1 over 4. Plug in your 2. 8 over 3 plus 4 minus 1 over 2. And we would have to put things together. Personally, if I was doing the mental math here, I'm going to just change the 4 cubed to 64 right away. If I was doing the mental math, I'd probably subtract the 8 over 3 from the 64 over 3 to begin with. Yes? Why is it an 8 right here? Why is it an 8 in the middle? Because I plugged in the 4. So the first time you plug in the 4 for all of the x's, and the second time when you're subtracting you plug in the 2 for all of the x's. So 64 minus 8 gives me 56 over 3. 8 minus 4 plus 4. -1/4 plus 1/2. To me, those seem like easier things to put together. But now, in the end, if I'm going to add all of this, I do need a common denominator. What's my common denominator? 12. So I have to make this over 12, multiply by 4, make this over 12, make this over 12. $48 plus this, $272, $275 over 12. Nice. Show you some tricks on your calculator that you can use to check. So, whoops, go here, clear out my graph. I'm going to write the equation that we had. So the equation that we had was bracket x plus 1 divided by x all squared. Okay? So when I graph that, I can see what that graph looked like. I'm going to actually zoom out my window so we're only going to go from -1 up to 5. But I'm going to go up to 100 to see if I can see more of the graph. There we go. Now, we wanted to find the area between 2 and 4. Your calculator, if you go to second calculate, number 7 has an integral. You can push number 7. It says, where would you like to start? I like to start at 2. Where would you like to end? I'd like to end at 4. It'll even shade it in, not crayon, a little disappointing. But you get 22.916. I'm going to go second answer back to this screen, gets that answer again, which is really helpful, instead of having to remember all those decimal places. And I'm going to hit the math button and change it to a fraction. Okay. That's where I always get nervous, because if I get a completely different answer, I have to say, sorry guys, I made an error somewhere. And it's like a really embarrassing video for a long time. But luckily, it works out to the same. So either I'm right, which I think I am, or I've somehow developed a program on your graphing calculator to give you the wrong answer, just like I do, to save my integrity as a teacher. Either way, I'm okay. So your calculator can be used to check an answer. You can find the area under a curve on your calculator as well. For the most part, though, you'll be asked to show your work and how you would calculate it using the definite integral. So I have some of those calculator instructions on the side there for you as well. Okay. I'm going to get you to try C. So I've put up the answer there so you can check how things were going. I have a couple of little notes along the way that the natural log of 1 is 0. I typed e cubed over 3 minus 2 natural log of 2 minus 1/3 into my calculator. I got 4.97. If you have a graphing calculator and you want to check if that works, you could type that into your calculator as well. And I've got a little picture of the graph showing that it also comes up as 4.9. I guess it's 4.98 if we're rounding correctly. Good save. So, first of all, The integral will be negative cos of 3x, because the derivative of cos is negative sine. And you write it from pi over 2 to pi over 6, plug in your values, and something interesting happens. Okay, you can ignore, you can ignore this right now. It's just me thinking about solving sine 3x equals 0. But I'll talk about that afterwards. But if I plug in my values, cos of 3 pi over 2 is? And cos of pi over 2? They're 0. We get 0 minus 0. Oh no. That's equal to 0. So something that's a couple interesting things. The calculator calculated the answer to be negative 1.07 e to the minus 14. That e to the minus 14 is scientific notation, which I could write with 13 zeros before I write that 1. What does this answer look really, really close to? 0. In fact, doing the calculus, I know the actual answer should be 0. The calculator itself has a program built in to calculate it little bit by little bit. And once it feels it gets close enough, it stops. So the calculator is not actually perfectly accurate here. Its answer is a little bit off due to error and due to it getting tired. Your calculators sometimes get tired, and they're like, you know what? This answer is close enough. If they're not happy with it, they can go somewhere else. But that's how close they got. We know the actual answer is 0. Now, this seems problematic because we're supposed to be finding an area under the curve. If we drew a picture here, we've got a black area there and a black area there. So something about the definite integral that we're going to learn from this example. The definite integral, whenever you find an area above the x-axis, it always counts that as positive. And whenever you find an area underneath the x-axis, it always counts that area as negative. In this situation, we have part of the area above and part of the area below. And they just so happen to be exactly the same. So one subtract the other one canceled everything out, and we're left with 0. So we can see that this area and that area would cancel each other out based on symmetry, and it's equal to 0. Off to the side here, I was just thinking about where do I have my x-intercepts? If I was graphing sine of 3x, well, I say to myself, when is sine equal to 0? At 0 pi and 2 pi. So 3x would equal 0, pi, and 2 pi. If I wanted to solve for x, I'd have to divide each of those by 3. So just a little review of solving within a sine equation. All right, so we got 0. Love that solution. Doesn't that look like a nice picture? Make you happy, right? Although that guy doesn't look happy because he got 0 as an answer. So first we integrate. And since the numbers were 3 to 2 here, they go 3 to 2 on the outside. We have to add 1 to the exponent and divide, but since we also have a chain rule inside, we'd have to divide by that 2 as well. Subtract our two things. Plug in 2, then plug in 3. And we get negative 1/10 to the 5th over 10 minus 1 over 10. Subtracting them both gives us a final answer of negative 1 over 5. Now, if we think about if I go to graph this, the graph looks something like this. And if plugging in 3 gives me the area all the way down to 0, and plugging in 2 gives me the area all the way down to 0, subtracting them in one way will give me the negative of subtracting them in the other way. So for example, using nice numbers, can you see that if your area from 3 to 0 was 7, and your area from 2 to 0 was 5, if you wanted to figure out the area between 2 and 3, it'd be 7 minus 5. But if you wanted to do between 3 and 2 and subtracted, you'd get 5 minus 7, you would get negative 2 instead of positive 2. So what happens is when these numbers are switched, you get the same answer as you would have otherwise. It's just these two values get flipped. And so from this, I could tell, looking at this, that if I wanted to find the area between 2 and 3 of this exact same thing, it would equal positive 1/5. If one of the answers is negative, the other one would be positive. Just the rules of how subtraction work. This will be one of the properties that we'll look at the end. So we have one more example that I'm going to get you to try. Well, let's see how you did on this last one. Integration. Get x squared over 2, and then e to the negative x would stay e to the negative x. You divide by -1, which makes it adding instead of subtracting. Plug in your values. Simplify. And you get -1 minus e squared. So what this example looks at is you can go into negative numbers as well. If you were worried about that, you can do definite integrals into the negatives as well. So at the top of the next page, we run into a bunch of properties of the definite integrals. A lot of them are similar to properties of integrals that we already know, but some of them are different. So if you went from a to a with a definite integral, your area is not actually changing. And so that would equal 0. We talked about going from, wait a minute, yeah, a to b and b to a. If we switch our numbers, the answer that we got in one will just be negative in the other one. If you have a value in between a and b, like c, the area between a and b will be the same as the area between a and c plus the area between c and b. So you can split up your definite integral and do it in 2 different parts. This will be important later on if we don't want to have part of it negative and part of it positive. If you have some constant inside your integral, just like in definite integrals, you can bring that constant out in front and evaluate everything like you did before and just multiply by that constant in the end. So in the green off to the side, if I wanted to find the integral between 0 and 1 of 2x, I could bring that 2 out in front. Doesn't really help me in this case, but maybe in some situations it would. I could find my definite integral value with that 2 out in front all the way through and multiply by 2 in the end. It'll give me the same answer as if I kept that 2 inside all the way. And just like in definite integrals, if you're adding and subtracting, you can do each integral separately.